Good morning, guys. So welcome to lecture 2. This is the acid-base definitions. I'm going to get through this and then we will record stuff for this coming week. So lectures 3, 4, and 3 and 4, because we only have Wednesday and Friday. So 3 and 4 will get done. I will go back and do 0 after that, and then I will make sure that you have everything you need moving forward. I don't want to be behind again because that's not fair to you. I will be moving the first test and I have not decided yet when that's going to be, so I will make sure that I get that notified to you as soon as possible. So let's take a look at our acid-base definitions. So the first thing we're going to do is talk about a review from some of the materials that we've been talking about. So it says that baking soda, sodium bicarbonate, undergoes thermal decomposition as follows. 2NaHCO3 solid goes to Na2CO3 solid plus CO2 plus H2O gas. CO2 gas, H2O gas. Would we obtain more CO2 and H2O by adding extra baking soda to the reaction mixture in a closed vessel or an open container? Why? So the reaction that I'm looking at is this one. 2NaHCO3 solid going to Na2CO3 solid plus CO2 gas plus H2O gas. And they've asked me, would I be able to get more CO2 and more H2O by adding extra baking soda in a closed vessel or an open one? And why? Okay, so there are a couple of things that I know from looking at this. Based on Le Chatelier's principle, in theory, if I add more baking soda, I should be able to drive this reaction forward, and I should be able to get more of the products. One of the other things about Le Chatelier's principle is that if I get more of these products, because these two are gases, the more space I have for them, the better that's going to be. So in theory, an open container is better. And it turns out that an open container is better because it drives that reaction forward because we have no product that's left over. It all goes away. In the closed container, it's all contained. And so we have less driving force to move forward because we're increasing the pressure as we generate that gas. So we're going to generate more of it. The reaction will be more driven forward in an open container. The only other thing I'm going to say to you is that the amount of NaHCO3 that is present has nothing to do with this. It has everything to do with the kind of container that we're in. And the reason that I say that is because NaHCO3 is a solid. So its amount, the amount of it that we have, is not relevant in looking at the equilibrium state. Okay? So the only thing we need to worry about is whether that gas is contained or not contained. When it's not contained, that means it's a lower pressure, so we can drive that reaction forward. It's almost like taking out that gas, the CO2 and the H2O that we're producing. It's almost like it disappears. And it doesn't really, it's just that our system is so large that we don't have to worry about it. Okay? In a closed container, we definitely feel that effect. All right? So that's that. When we talk about the next one, we are supposed to be considering the following reaction at equilibrium. A, gas, goes to 2, B, gas. And from the data shown here, calculate the equilibrium constant, both Kc and Kp, at each temperature. Remember that Kp equals Kc times 0.0821 T delta N. All right, fine. So I'm supposed to calculate a Kc and a Kp at all of these temperatures. So I'm actually going to move this to, I'm going to move this down a little bit. So I'm going to look at what my concentrations are at 200 degrees. So this is not an ice table, but it looks similar to one. 0.0125 molar, 0.843 molar. I have at 300 degrees, I'm just copying that table. 121, 0.764. And then at 400 degrees, I'm looking at 0.250 and 0.724. I know that my Kc is equal to the concentration of my product, B, raised to its stoichiometric coefficient 2 over the concentration of A. I also know that if I were to write a Kp, that would be equal to the pressure of B squared over the pressure of A. Okay. Now, since I have concentrations that I've been given, these numbers are all concentrations of molarity, I am going to start by calculating Kc at each of these temperatures. Okay. So Kc here is going to equal the 0.843. That's going to get squared. We'll divide that by the 0.0125. Okay. 0.843 x squared divided 0.0125. And that gives me 5, it's actually 56.85 is the number that I get out of that. I'm going to calculate Kc for the next temperature, and that's going to be my 0.764, that's going to be squared, over 0.171, 0.764 x squared divided by 0.771. That gives me 3.41. And then Kc at 400 degrees is going to be the 724 squared over 0.250. So 0.724 divided by squared divided by 0.250. And that gives me 2.10. Okay, so those are my Kc values. Now I've calculated all the Kc's. Now I can start looking at what are the Kp values. So Kp, when we look at the 300, is going to be equal to Kc times 0.0821 times the temperature, and these are listed as degrees C. And this is actually not 300, this is 200. Sorry, I thought my first temperature was 300. So that's at 200. So we'll multiply that by 200 because these are, that's degrees C. I need to convert that. So I need to take that 200, I need to add that to 273. Then I'm going to do the delta N. And the delta N here, remember, we're looking at the number of moles of product minus the number of moles of reactant. So delta N is equal to 2 minus 1 equals 1. Okay, so that's my delta N. Awesome. My delta N being 1. I'm going to take my Kc, the first one that I calculated, as 56.85. I'm going to multiply that times 0.0821. I'm going to multiply that by 273, 200 plus 100 plus 273. $56.85 times 0.0821 times 200 plus 273. And that gives me 2.21 times 10 to the third when we talk about the Kp. At 300 degrees C, our Kp is going to equal our Kc times 0.0821 times 300 plus 273, and that's to the first power. So the Kc that I had here is 3.41. 56.85 goes here. And 3.41 is the Kc here. So 3.41 times 0.0821 times 273 plus 300. And that gives me 1.60 times 10 to the 2. Our last one at 400 degrees C, Kp, the Kc that I calculated was the 2.10 that you can still see right here. So 2.10, multiply that by the 0.0821, we'll multiply that by 400 plus 273. So 2.10 times 0.0821 times 400 plus 273. And that gives me 1.16 times 10 to the 2. Okay. Now, again, since we have 1 mole of gas difference, I do expect that there will be an effect because we're in the pressure, all right? So Kc is not going to equal Kp, but we don't have to worry about factors for that because of the equation that we've written, okay? So those are my Kps and my Kcs for review 2, okay? Hopefully there are no questions about that, but if there are, you know how to contact me. Let's talk about 3. So review 3 says, for the reaction H2 plus CO2 goes to H2O, all of them gases, plus CO at 700 degrees C, Kc equals 0.534. Calculate the number of moles of H2 that are present at equilibrium if a mixture of 3 moles of CO and 3 moles of H2O is heated at 700 degrees C in a 10-liter container. That's a lot of information. So I'm not sure exactly where to start. So I start by writing down my equation. H2O gas plus CO gas. We're at 700 degrees C, and my Kc equals 0.534. Okay. Calculate the number of moles of H2 present at equilibrium. Oh, Lord. We're looking for equilibrium. That means that this is an R, this is an I, this is a C, this is an E. I want to know about H2 at equilibrium. If a mixture of 3 moles of CO, 3.00 moles of CO, and 3 moles, 0.300 moles of H2O are in a 10-liter container. And so each one of those concentrations is 0.3 divided by 10, so that's 0.03 molar, 0.03 molar. Notice that I don't have any of this listed and I don't have any of that listed. So looking at it the way that it's written, we know that in order to make H2, we're actually going to be looking at the reverse equation, right? Because I have to break down these, what's written here is products, the H2O and the CO2, or the CO and the H2O, and I'm not, can I do it? Yes. Am I going to do it? No, I'm not. The way that I'm going to handle this is I'm going to move this up a little bit, and instead of doing that thing there, I'm going to say, all right, let's talk about CO gas plus H2O gas going to give me CO2 gas plus H2 gas. That's my reaction. If I were to write an I know that the initial concentrations of each of these, because I calculated them previously, is 0.03 molar. 0.03 molar. This is 0, this is 0. I'll have a C, and I'll deal with that in just a second. What I'm looking for is this product right here, okay? So my change is going to be a negative x here and a negative x here. Both of them have a 1 in front of them, so it's going to be a negative x. This one is going to be a positive x, and this one is going to be a positive x. Both of them have a 1 in front of them, so that's what I would be looking at there. Now my Kc expression for this equation is going to be H2 times CO2 over CO times H2O. And I don't have a value for that. What I have a value for is the one for the reverse reaction. But remember we talked about this. If I want to find the Kc for this reaction, and I know the one for the reverse, I can take 1 over that Kc, and that'll be the value that I need. So I can take 1 over that 0.534, and that will be the number that I'm looking for here. So 1 divided by 0.534 is going to give me 1.87. Now, I know that H2 is an X, the CO2 is an X, the CO and the H2O is a 0.3. Both of them are, so I'm going to write that down and square it. I can then take 1 point, and I'm actually going to do it the other way. So I'm going to move the this is going to become x squared equal to 1.87 times 0.030. I added an extra 0 squared. So 1.87 times 0.03 squared. And that gives me 1.68 times 10 to the minus 3. I need to take the square root of both sides in order to get an x. So I take the square root of that answer, and that gives me x is equal to 4.10. And actually, it should just be 4.1 times 10 to the negative 2. And that's the concentration that I would expect for H2 at that temperature. Okay? So that's how I would solve that. And again, I'm looking at how do I take the information from that question and put it into that rice table, because that helps me to keep track of what I have, what I don't have, and what I need to do to be able to solve this. Okay? Now, could I have done this again? Could I have done this with this table here? Absolutely, you can. The way that this would have worked, either you put this in as a positive x and a positive x and a negative x here and a negative x here and go about it that way, or you can move it the way that I did it to look here. Now, I know that in theory this should be 0.03 minus x, and again this should be 0.03 minus x, but we've made the assumption that the x is small, so that's how we solve that. Okay, so hopefully there are no questions there. Let's go ahead and talk about the next question that we have. The equilibrium concentration constant, Kc, for the following reaction is 1.2 at 375. N2 plus 3H2 goes to 2NH3. What is the value of Kp for this reaction, given that equation? All right, let's start at the beginning. So we're talking about N2 gas plus 3H2 gas going to 2NH3. You're given a Kc, and it's 1.2, and that's at 375 degrees C. 375 plus 273 is 648 Kelvin. Okay. Yay. What is Kp? So Kp is equal to Kc times 0.0821 times the temperature to the delta N. Okay. Delta N here is going to be the 2 minus the 3 plus 1 is 4. Remember, that's negative 2. So if I start plugging things in here, I'm solving for Kp. The Kc I was given is 1.2. Multiply that by 0.0821 times the temperature, 648. And that product is raised to the negative 2 power. Okay. So I can do this. I can say 0.0821 times 648. I take and I raise that to the negative 2 power. I then multiply that by 1.2. And that gives me 4.24 times 10 to the minus 4th. And actually, it should be 4.2 for sig fig, because I only have 1.2 for the Kc that I was given. Okay. So what is the value of the equilibrium constant for the reverse reaction? So one of the questions they asked me, what is the K value, Kc for the reverse reaction? Kc for the reverse equals 1 over the Kc for the forward. That's equal to 1 over 1.2, which is equal to, divided by 2, 8.3, 0.83. Okay. So that's that one. What is the value of the equilibrium constant? No, I got that one. And the value of Kp. What is the value of Kc for 1/2? And they want the Kp for this as well. So again, Kp is going to be equal to the Kc, the 0.83 that I calculated, 0.0821, 648. And then we have to look at delta N. So we've reversed this equation, right? So we've got products 4 moles minus 2 moles. That's actually squared. So that's squared. And that's our delta N for the reverse reaction. So 0.83 times 0.0821 times 648. The product of 0.821 times 648, excuse me, is squared. We do all that happy math, and that gives me 2.35 times 10 to the third. Again, that rounds to 2, so 2.4. They then want to know, what is the value of Kc for half an N2 plus 3 halves of an H2 goes to NH3? Okay. So the first equation that I had, the N2 plus the 3H2 going to 2NH3, that first equation that we wrote down, we're going to take that and divide that by 2. So when we take that first equation, the Kc for this initially was 1.2, but when we do the inverse of that, or sorry, when we divide it by 2, we need to raise that to the 1/2 power. Okay, so we're taking the square root, and that's equal to 1.25, and I get 1.09. Okay. So again, this is about understanding what do we need to do with the mathematical value that I've been given if the reaction is the forward one and I change the stoichiometry, or if it's the reverse one and I need a number for that, and then how do I calculate Kp and Kc? Now they do want Kp for this as well, so I'm going to scroll up a little bit. I know that Kp is equal to the 0.0821, oh wait, I forgot my Kc, sorry. My Kc, which is 1.09 times 0.0821 times the temperature, which is again still 648 if I'm not mistaken. Yeah, 648. And now our stoichiometry is a little bit different. So this equation that we just wrote, number of products that I have, moles of product that I have is 1. I'm subtracting from that 1/2 plus 3 halves, which is 4 halves, which is 2. So 1 minus 2 equals -1. Okay. Awesome. I can do that. So 0.0821 times 648. I take the inverse of that, and then I multiply that by 1.09. And that gives me 2.0 times 10 to the -2. Okay? So there, I have calculated a whole bunch of stuff related to the case that we looked at the last time. Questions, comments, problems. If there are any questions, comments, problems, concerns, any of that stuff, please let me know. Again, email, WebEx, phone, whatever. Let me know that you have issues and we'll be able to talk about that. I'm going to go ahead and stop the recording at this point, and I will be back in just a minute so that we can start on the next part of this lecture. Thanks, guys.